kids, welcome to the last unit of the semester. Right? Hard to believe that back there, beginning right last week of August, that we would be here, and this is exactly where we would be if we were in person. So just so much credit to all of you, right? In this very unusual circumstances, in isolation, computers, Zoom problems, boomer teachers who can't figure out the right buttons and sometimes to release and all that, assessments online, all that kind of stuff. And you've made it, you've done it. Keeping up with the work despite us not being able to formally assign them. You've done an amazing job. So Unit 6 is strictly mechanical, no applications. It is just a whole list of techniques, mechanical techniques of how to find an antiderivative or an integral, evaluate an integral. Okay, both of those things mean the same thing. So let me give you the big idea for the entire unit. If you are given area between a curve and the x-axis, and we had this in a warm-up not too long ago, where we talked about collecting all the area from here, from -3 to 5. And I told you that function was x squared. You could approximate that with rectangles and trapezoids and all that kind of stuff, but you could not find the exact value, which was 50 2/3, without your calculator. You used Math 9. You want to be able to figure out a way where I give you A and B, the integrand, and you come up with the sum of all those infinite rectangles, right? Infinitely thin rectangles. You want to be able to do that without your calculator. That's one. That is evaluating a definite integral. And I want you to notice a root word in here. Look at me going with my English. Finite. Start at -3, stop at 5, you get a number as an answer, a definite integral. But I'm also going to teach you how to evaluate an infinite, or a indefinite, I should say, not infinite, indefinite integral, sometimes called the general antiderivative. So why this is useful is without any limits of integration, right? Notice I don't tell you to start or stop anywhere, but I give you an integrand and I want you to come up with an algebra expression that I can use for any start and stop, right? Instead of having to constantly anti-differentiate, what if you give me an algebra expression and teach me how to use it so that I can come up with 50 2/3 when you give me -3 and 5, but a different answer when I give you 5 to 50, or when I give you -10 to -3, right? I want to be able to use it over the algebra expression over and over again. So I'm going to take care of both of teaching you how to do both of these things today. And then for the rest of the freaking unit, I'm just going to teach you how to do it with different integrands, right? How do I go the rule when I have an x squared, the rule when I have a trig expression, the rule when I have a quotient, the rule when I have a product, the rule, right? I'm going to give you the rule for all different types of integrals. But after today, You're going to know how to do a definite integral and an indefinite integral. And the only extra learning you have to do is what formula do I use? What process do I use for the particular integrand, which is what's inside the red box? Okay. So let's start with a prequel. Is that how you spell prequel? Prequel to dealing with antiderivatives is first I want you to look at these derivatives. So notice I've called these capital F, G, and H. To take their derivative, I hope this is not a big deal for you, right? This is really to the 1/3. So in each one of these cases, I'm going to bring down the 1/3. I'm going to copy over the middle. And subtract 1 from the exponent. But what am I forgetting? Right? Power down, copy over the middle, subtract 1 from the exponent, and the chain rule, right? So this is actually, the derivative of 2x plus minus 1 is 2, right? So I actually have 2/3 2x minus 1 to the negative 2/3. That is the derivative of capital F. Well, what's capital G prime? And what's capital H prime? F, G, and H are different, but they only differ by their constant, don't they? Plus 0, plus 5, minus 6. So all of these functions are all cube root functions. And they're all cube roots of the exact same function, 2x minus 1. Meaning when in the derivative, the negative 2/3 is all on 2x minus 1, and each time you're being multiplied by 1/3. What happened to the derivative of the 0, the derivative of the 5, the derivative of the negative 6? The derivative of a constant is 0. So everybody's derivative is the same. How many more functions in this family have the same derivative? An infinite, right? That's like having, right? That's like the Getzes, right? This is Mr. Getz. This is me. This is D1, our first child, right? D2, D3, D4, D5, and D6. Oh, D7, which is our Duke, right? We're all Getzes. We're all Getzes. We're all different, right? We differ by a constant. So there's a whole family of functions that have the same derivative. Remember what a derivative does. It describes the slopes on a function. Well, if you just take this function and then shift it up 5 or down 6 or whatever, however you want to vertically translate it, it does not change the slopes, right? At any particular x, the slope is the same because you just move the graph up and down. So the idea of this prequel is every derivatives come from a family of functions. A family of functions, and that family has the same last name, Getz, or cube root of 2x minus 1 to the 1/3, differ only by their first name, or in this case, the constant. Oops, by a. Okay? Every derivative you've ever done, any derivative, actually represents a whole family of functions. And that family has a whole bunch of individual members, and those individual members is just some constant. So why that's a prequel is because our job now is to go backwards. Now, given the derivative, so this was the original, given the derivative, find the family. Okay, so you have to undo the derivative. Isn't that what an antiderivative does? AKA undo the derivative. So remember, all of these family members had the derivative times 2, because of the chain rule, plus some constant. This is a derivative. Undo it and go back. Well, think about what we did. We took the power down. How are you going to get it back? How are you going to undo power down? Power up, baby. Power up. So there is a whole family of functions with the same derivative. So we just need to find the rules to get backwards. Sometimes I don't need any rules. Sometimes I can just see it. Remember, everything that's in my box is derivative. I'm taking the derivative of capital F, taking the derivative of the left side and the right side. I took the derivative, I differentiated, and I got F prime is equal to power down, copy over the middle, subtract 1, spit out the derivative of the inside. To go backwards, I'm going to undo the derivative. Who undoes the derivative is the antiderivative, and you have to do the same thing on both sides. So I'm going to take the antiderivative with respect to x of the left side, and then I'm going to take the antiderivative with respect to x of the right side. And all that means is undo the derivative. Put that power back up, put the 2 that came spitting out with the chain rule, suck it back up, and that's what I have. Almost. Because the original could have been not plus 0, but plus 5. Or it could have been the one that's minus 6, or it could have been a lot of others. So we say the family name is the cube root of 2x minus 1, and then there is the individual constant. Okay, kind of cool. Notice I don't have any, I'm just saying, right, I didn't ask for a number. There's no limits of integration here. I took an antiderivative, which means undo your derivative here, get back to an algebra expression. Crazy, but that's all it is. Take an integral expression, turn it into an algebraic expression. And remember, there are an infinite number of them that only differ by a constant. So find the general antiderivative means no limits of integration. Means your antiderivative is an algebra expression. And the whole first handout that you're doing is just giving me algebra expressions. So no rules. Can you just visualize what's going on here? If your derivative is a constant, what did it come from? Right? Technically, that's an x to the 0. What did it come from? Check your guess. I say it came from x to the first. How can I check my guess? What can I do? Oops, sorry. Check my guess. right? If I, when given a derivative, so I'm saying f of x is equal to 1, and I want to, if I'm telling you that's my derivative, what's my antiderivative? My antiderivative is just x. Check your work. Go backwards. What is f prime? Is 1. Do they match? Yes, then I must be right. However, I could have had any constant here, right? Because f prime would still be 1. All right. What if I said your derivative was linear? What's the antiderivative? What's your guess? If your derivative is linear, didn't it come from a parabola? Okay, I'm used to this now. This is going to be, right? Done and done. Ooh, maybe I better check my work. I'm still new at this. Oh, oops, what's the derivative? 2x plus 0. Oh, that doesn't match. Oh, what if I divided this by 2? Would it match now? Oh, turn that frown upside down. Wipe away those tears. How about if you started with a quadratic? What did it come from? What did it come from? This is the derivative. The derivative is x squared. What did it come from? Something cubed, right? But can you see what happens if you just say, oh, it came from x cubed plus a constant? Is that right? Check your work. You can always check your antiderivative by taking a derivative. No, f prime would be 3x squared. But how about that? Now I get the antiderivative of x squared must be 1/3 x cubed, or x cubed over 3, however you want to write it. Why must it be so? Because when I take the, it's like somebody who said to you, hey, 3 into 24 is 8. And they would say, well, how come? And you say, well, because I divided. How I undo division is multiplication, right? So how come 1/3 x cubed plus c is the antiderivative of x squared? Because when I take the derivative, I get x squared plus 0. Check and check. That's why. No other reason. Well, I think I'm starting to see a pattern. Do you? How about if I started with my derivative is a cube? What do you think the antiderivative is? Check your work if you're not sure. Whoops. So can you make a rule? If you are given x to any power, what is the general antiderivative? X to the n plus 1 divided by n plus 1 plus a constant. I call this the power up rule, baby. Right? Not power down. If you took to take a derivative, you power down. To undo that, you got to power up. But you have to divide by the power up. Power up, divide by the power up. See if that works. Oh, psst. Domain never goes away. This doesn't work if your power is -1. Doesn't work. We never had that situation with derivatives. I never gave you a derivative rule and said, by the way, it doesn't work when, right? This derivative rule works for, yes, any number except for -1. And how come? Because you're dividing and you can't divide by 0 anytime, any place, anywhere. So this isn't an integer. But can you, if f of x is if this is the derivative, what's the antiderivative? What did it come from? X to the power up. Add 1. Divide by negative u. Please don't leave it like that. Okay. I don't care what you do with this. You could write it as negative 3 over x to the 1/3 plus c. You could write it as negative 3 over the cube root of x plus c. But please do not leave fractions. Clear fractions within fractions, okay, no matter what you're doing. New notation. Instead of telling you that I'm giving you a derivative, I'm going to put integral notation around this, and you are responsible for knowing that what's inside is a derivative, and I'm asking you to undo the derivative. Since I have an exponent, how I undo it is power up. Family name, individual name. So how about this? I'm going to tell you that this is a derivative, but I'm not going to tell you in words anymore. I'm going to tell, whoops, I forgot my dx. I'm going to tell you with symbols. So you have to know this function is a derivative, undo it. Now you're actually going to use a property of integrals, right? You're actually going to do the integral of a sum is the sum of the integrals. Power up, divide by the power up each time. Undo it, and you have x cubed over 3 plus a constant. You have plus 10x squared over 2 plus another constant minus power up, x to the 0. Power up is x to the first over 1 plus your last constant. One constant plus another constant minus another constant is still just a constant. So this final answer is how can you check your work? Take the derivative. To check my work, take the derivative of this. The derivative of 1/3 x squared, x cubed is x squared. The derivative of 5x squared is 10x. The derivative of negative 2 is negative 2x is negative 2, and the derivative of a constant is 0. Check. Sweet. Remember, you don't have any limits of integration because you are coming up with a general antiderivative. Collecting area under x squared plus 10x minus 2. Remember, I forgot my dx. Collecting area under the integrand. The integrand is the derivative. Creates this family of functions that is cubic that only differs by a constant. So I'm going to give you some rules. So that's your power up rule. That's when you have an exponent that is not negative 1. The antiderivative of sine x, well, think about this. What's the derivative of sine? Derivative of sine is cosine. So if I had sine, what do you think I came from? right? Is that right? I don't think so. What is the derivative of cosine? The derivative of cosine is what about this though? Check your work. What is the derivative of negative cosine x plus c? Sine x, right? So what is the antiderivative of cosine x? Plus c. Here's our osmosis rule, right? What is the antiderivative of 3 sine x? Take this 3, osmosis it through the integrand sign. Really? I'm asking you, what is 3 times the integral of sine x dx? Negative 3 cosine x plus c. Uh-oh, this is a dagger. This is a dagger. That's a composition. What if that's my first guess? If that's my first guess, which is not a bad guess, is it right? How do I know? Take your derivative. Check it. What is the derivative of this? The derivative of this is negative sine 3x times 3. When you have a composition and you take a derivative, you have to spit out the 3. So what is the undo of spitting out or multiplying? Take that derivative and you will get sine of 3x. So let's make a sheet. Okay, make a list. You're going to want an antiderivative list. So here are the formulas that you're going to be adding to all freaking unit. Your power up, divide by the power up rule. Write that down and write down that it does not work if your exponent is -1. Here is sine of any number times x, right? Where you have a composition. So there's sine and cosine. Right? It's not power up, divide by the power up, but it is taking care of, you have a composition. When you're taking a derivative, you would multiply by this k. So when you're going backwards, you have to divide by that k. I'm going to give you some other ones. And I really should have had the k in here as well. I just forgot. The antiderivative of secant squared is tangent. So yes, if I had a k here, it would be over k. Okay. Now, you should be asking yourself, normally when I give you trig information, I go sine, cosine, tangent, then cosecant, secant, cotangent. And I haven't done that. I went from sine and cosine, bizarrely, to secant squared, cosecant squared, and secant tangent. Can you see why? What is the derivative of tangent? The derivative of tangent is secant squared. What is the derivative of negative cotangent? Positive cosecant squared, right? These are direct rules. Oh, I forgot I had one more. There's your 6 in the antiderivative side. Sine, cosine, tangent, cosecant, secant, and cotangent. I gave you all 6 trig functions, their antiderivative. Notice, just like before, all of our negatives, right? Negatives start with C. That's a memory trick. You can always, always check your work by taking the derivative. Notice I have not given you these formulas, and I'm not gonna, not for a while. There is no direct rule for finding there is no power up rule that I'm going to give you for x to the n, or for how to anti-differentiate tangent or anti-differentiate cotangent. Think, there's no derivative rule that just ends with tangent x, no derivative rule that just ends with cotangent. Okay. But we have a nice list so far. Sorry. This is our general antiderivative formula list so far. Now that you have this list, minus these, right? You don't have these. I can now ask you to do definite integrals. I want you to integrate now with an A and a B and not use Math 9. Now this one, I don't need Math 9, but I also don't need an integral rule, right? This is a trapezoid right here. I can use geometry to figure that out, right? 1/2 the height, which is 4, 1, 2, 3, 4, and this plus times the sum of the bases, right? This height is 3, and this height is 5.4. I just figured that out by putting, right, those in. And I got 16.8. Look at the units on there, though, right? Because this is meters per second, and x's are seconds, so I got meters out of that. I integrated velocity, and I got distance. Whoa. Integrate velocity, yield because of the units, right? We've been talking about this in Unit 5. Now, let's pretend I didn't think about geometry. Evaluate a definite integral. Oh, no, I don't want a definite integral. Look, I took off the a and the b. I just want you to use your rules to do the indefinite integral. Power up, right? Isn't this a 1? Power that you're going to osmosis the 0.6 outside, so it's just going to be 0.6 x squared over 2 family name plus c. But that's just 0.3 x squared plus c, isn't it? Which is a parabola. Forgot that I wrote that. Integrate the velocity function. Hey, without limits of integration, I got not just a family of functions, but I got infinite distance functions that I can use when x is 5 to 9, or when I can use a lot of different ways. So look at this constant. Here is the parabola. Now it's not the whole parabola, right? But at 0, what if my constant was -2? There is the parabola starting at time equals 0. What if that constant was 4? 0.3 x squared plus 4, that's the parabola. But can you see how the slopes on that parabola never change? There's if the constant is 0. So when you're integrand, when you're taking the antiderivative of the integrand, you come up with the family name plus c. All right, well, wait a second. At time equals 9, how many meters have I gone? Right? Use your position function. Capital F of 9. Plugging 9 in here, right? 0.39 squared plus c is 24.3 plus my constant. How about at 5? What did you get? Plug in 5, right? I had a velocity function. I came up with a distance function. So I said, how far am I at 9? How far am I at 5? Oh, what if I want to know how far I am? How far did I go between 5 and 9 seconds? What would I do with these two values? Wait, what? Wait, what? What? Let that sink in. Let that sink in. Wait for it. To find the value not of an indefinite, but a definite integral without using Math 9 or geometry, you find the general antiderivative and then plug in the limits of integration and subtract. You've done it, babe. You've done it. No Math 9. You have evaluated your first definite integral. So hopefully you could see by that subtraction that the c's subtract out. I don't need to worry about the c when I'm doing a definite integral because, and if you want to do this with your calculator at some point, right, if you want to pause and put this in your calculator, and y1 I have 0.6, right, which is the velocity, 0.3x squared plus 0 is my distance. When I plug in 9 and 5 into the parabola, I get a value for y of 5 and a value for y of 9. But when I subtract that distance between them, I get 16.8. Look what happens when my constant is plus 2. When I plug in 5 and plug in 9, I do not get the same values. I don't get these exact same values, but you know what happens when I subtract? The vertical distance between is still 16.8. I made my constant plus 5, right? In y2 is capital F. Capital F of 9 is different. Capital F of 5, I'm sorry, that one's 5. 5 and 9 are different. But when you subtract them, the distance, the vertical distance is always 16.8. Whoa. That leads us to the integral evaluation theorem. As long as the integrand, I just need the integrand to be continuous, not differentiable. The integrand just has to be continuous on an interval. And if capital F, the undue, is any antiderivative, plus 2, plus 5, minus 100, minus 3, doesn't matter, any of the antiderivatives on that interval, then the definite integral, take the derivative, find its antiderivative, plug in, subtract. You technically have a plus c here and a plus c here, but you're subtracting and they go away. The vertical capital F of B minus capital F of A is the vertical distance between endpoints on an interval of the original function, original, not the integrand. Crazy. To evaluate a definite integral, take the antiderivatives, plug and chug, and subtract. So let's do these examples. right? And if you want to pause the video and do this and then check back and see if you have it right, taking the antiderivative of a sum is just taking the separate antiderivatives, undo x squared, power up, divide by the power up, plus, don't forget that's an x to the 0, 2x to the first over 1. I don't need the plus. You can put the plus c if you want, but I want to show you this notation. This means what comes before here is the antiderivative, and I'm going to plug in 6 and plug in 1. Most of the mistakes after you learn these, most of the mistakes are computational. Okay. I leave you to do that. How about sine x? What is the antiderivative of sine x? Negative cosine of x. Evaluating at b and a. You can osmosis that negative out as well if you want. You don't have to. And then, of course, I have the exact same, if I have the exact same integrand, I have the exact same integrand, so I'm going to have the exact same antiderivative. And yes, that's reducible. I just had the same denominator for you. Okay? Done and done. And again, I'll leave those to you to practice. And the last thing I'm going to do with you, the last example of the definite integral, is I want you to find area under this curve. And you are used to finding, right, the area under a curve between the curve and an x-axis as long as you are positive, right? I'm just going to have to integrate, but I cannot integrate from 0 to 2. Why can't I? My bounds change, right? When you're drawing rectangles, the height of your rectangle here, right? The bottom is the x-axis, but the top is the square root of x. But over here, all the rectangles, the bottom is the x-axis, but the top is x squared. If your boundaries change, your function changes, you have to change the integral, but that's okay. I'm continuous. So the integral from 0 to 2, which is going to be equal to the area because my function is all above the x-axis, is 0 to 1 plus 1 to 2. My first function is x to the 1/2, and my second one is x squared. I don't need a calculator anymore. I know how to do this. I am going to fundamental theorem this by treating the x squared as a derivative and telling you where it came from, and x to the 1/2. So x to the 1/2, power up, add 1, and I get 3/2 divided by 3/2. Please don't do that. And I'm going to evaluate this at 0 and 1, plus power up, divide by the power up, evaluated at 1 and 2. So you can take the 2/3 to the outside if you want. And you're going to have 1 to the 3/2 and 0 to the 3/2. I like that situation. Here, I'm going to have 1/3 on the outside, if you like. And I'm going to have 2 cubed minus 1 cubed. Again, I leave that to you to clean up. But the important piece there was you had to understand that the boundaries of the rectangles you're drawing changed. So I had to change my integrand, which means I had to split up the integral. That's okay that this is a piece. This is not a nice piece. I don't need differentiability. I can still integrate and find the area because this function is continuous. That's all I needed. Okay, so you have a whole bunch of problems to practice. You have integration homework, integration handout number 1, which is all indefinite. All of your answers better have a plus C. And then you have integration number 2, which is all definite. You can check all of these with Math 9. Note, though, on an assessment, you either won't have a calculator or you're going to be asked to show the setup, right? I don't really need to assess whether you can add those fractions, right, and come up with the right answer. Okay, so we've given you a ton. I would do again, we can't collect any of it, so I would either pick the odds or the evens. You don't necessarily have to do them all, but do as many as you feel getting used to it, right? Or pick and choose, right? And say, oh, I haven't done one that looks like this before. I'll try that one. Oh, this number 11 looks a lot like number 10. I'm not going to do number 11, right? That kind of thing. Use your judgment, right? I can't collect any of it, so use your judgment. Get as much practice as you feel like you need. All right. I will see you in our next live session.